All right, hello everyone, welcome. So I am Dr. Conrad Allen. I am a senior research engineer for Georgia Tech Research Institute. And today I'm going to be talking to you about artificial intelligence empowering robotic understanding of poultry processing. In engineering, we have a rule that the longer your title is, the more intelligent it's going to be. So you have to fill it up with lots of words, and that way you know people know it's going to be good. So a little bit about me. I think it's really important to understand the context of who's giving the presentation. So I have a bachelor's and master's in mechanical engineering from RIT 2012 and 2014. I got a doctorate in robotics from Georgia Tech in 2018. And since then, I've been working with GTRI and through GTRI ATRP on developing new and innovative ways of bringing robotics into the poultry industry. Now, I'm going to point out something very important about this slide. At the title, with all those very intelligent words, I have AI and poultry. When I talked about me, I am not a computer science major. I have never had a computer science class, and everything that I know about poultry I've learned since working for GTRI and with ATRP. I am not a specialist in poultry science. I am not a specialist in computer science, but I've worked with these technologies for about the past decade in my professional career. And through there, I think that I've gained some perspective on how to use these technologies, or how to use robotics in conjunction with artificial intelligence in order to do poultry processing. And that's really what my talk today is going to be about, is how do we utilize these technologies in such a way that we can overcome the gaps that started to arise due to the increased trouble of getting labor into these plants. Most of the work today is going to be, was developed under a USDA NIFA grant for the Center for Scalable and Intelligent Automation in Poultry Processing. I did not come up with that name, but this is through the University of Arkansas and is in collaboration with Fort Valley State, University of Lincoln, Nebraska, and us at Georgia Tech. The vision of the center is to incorporate these various advanced technologies into a system that allows us to create a food-safe poultry processing industry that is scalable and intelligent solutions to meet the rising national and global demand in poultry products. One of the things that you'll notice whenever you're talking about poultry production is you're talking about the scale of how many birds are coming through these plants. And part of the reason for why there's so many birds that are coming through these plants, in part, is because we need to feed America and the rest of the world, but also because it is so expensive to have these equipments, and the payout for each bird is so low that you have to do it at large volumes. If we want to be able to do the systems, if we want to be able to do these processes at smaller scales, we need more advanced technologies that are going to be able to be more affordable for smaller producers. And that's one of our goals, is to try and be able to create a system that can be used not only at the large scale production sites, but also at the smaller scale as well. So some of our motivation: manual labor is essential to poultry processing. It's about 88,000 Georgians employed in 2022. Now, for some of the younger folks here, that might sound like a lot, but for some of the older folks here, at the very least people who have been in the industry for a long time, you'll actually notice that that number is down. From 2012, I believe the number was closer to 110,000, so fewer and fewer people are in this industry, and it's become more and more of a problem in order to fill these roles. And of that 88,000, the majority of them are in poultry processing. So that includes everything, but for the most part, that's poultry processing. And it's not difficult to see why it's so hard to staff these jobs. The work is physically challenging. The environment is uncomfortable. These jobs are necessary for for us to have food at the table, and yet at the same time, it's getting harder and harder to find people who are willing to do this work. That being said, at the same time, robots are still having a hard time entering into this space. Automation struggles with unstructured environments. It's what robots are designed to be able to do, to be able to handle new situations and changing environments. But at the same time, these robots do their best work when they know what they have to do ahead of time. When they are welding a car door, where it's the same operation 100 times a day. When they're doing pick and place operations of things that have schematics, where you know what the part is down to the millimeter. These are areas where robotics are able to work really well. Once you put a robot in front of a chicken breast, it literally does not know what to do. It has a very hard time understanding what it is looking at, understanding where to grasp that object, and how to manipulate it. So what we are hoping is that artificial intelligence can augment robotics to tackle these uncertainties in poultry processing, to be able to bridge the gap and clear those uncertainties so that robots can do better processing and provide much of the needed labor in this market. And just for a bit of perspective, from 2019 to 2023, the private industry has invested nearly $500 billion in AI technologies. That's an estimate out of Stanford. I don't know exactly how they got those numbers, but that number might even be low. And in the past, in the last half of 2023, a third of the investment of 2023 was in large language models, things like ChatGPT. So there's a huge amount of investment in AI right now, not necessarily to solve these problems, but these are solutions that we can leverage in order to help our industry, in order to be able to overcome some of the shortfalls that robotics leaves behind, and to be able to meet the need of labor demands. However, if I'm going to be talking about how AI and robotics might be able to be used in conjunction to solve labor issues, it would probably be beneficial to talk about robots and AI. So what is a robot? Now, when you think of a robot, you're probably thinking of either a 6-joint manipulator, or you're thinking of maybe some sort of giant robot monster that attacks cities, I'm not sure. But in robotics, we have this fairly simple understanding of what makes a robot. A robot is the continuous cycle of sensing, decision-making, action, done by a machine, of course, where the robot has to be able to understand its environment, make a decision about what needs to be done within that environment, and then act upon it. If you get those things together, you have, classically, a robot. And if you think about something like a Roomba, you can conceptualize how this might happen. The Roomba senses the wall. It decides that it's not going to bump into the wall, so it turns and then sees that the space in front of it is clear, and it continues moving forward. One of the new innovations for Roomba, or at the very least something that they've been trying to implement over the past few years, is AI detection to make sure that if your lovely household pet is maybe not as good about waiting to go outside and has an accident, the Roomba can detect that and not smear it into your carpet. So these are the sorts of things that a robot is typically expected to do: sense, decide, act, and so on and so forth. However, due to the prevalence of microcontrollers and the advancements of technologies, that loop also fairly well describes a toaster oven. Modern toaster ovens are very advanced. They can sense, decide, act. And it also describes an airplane. And my point is that the definition of a robot has been diluted somewhat by these other advanced technologies that can also go through this cycle. Myself, I'm perfectly comfortable calling a toaster oven a robot, but other robotics researchers think that there needs to be further clarification. So there's been a push within recent years to add a component to this of what our understanding of a robot is. And that is to put this under the umbrella of a machine that can cooperate. And that brings up some very interesting distinctions on what a robot is. A robot is not just a machine that thinks for itself. A robot is a machine that's meant to cooperate with you to complete a task. And the idea that you can have machines working with people, working alongside people in order to do tasks, really recontextualizes how AI might be used in these fields in order for people to do jobs better with fewer man hours. So that's robot. What about AI? We've had a lot of people today talk about AI, and they've done a great job describing exactly the different areas that AI could be used and how AI is effective in these fields. But one of the things that I want to bring back and really think about from a 30,000-foot perspective is AI is at its heart a transform. It takes input from one domain or several domains, and through the use of optimization and training of weights and biases, it then outputs a probability. Now, I know that we have a lot of scientists in the room, and I think that that's very important to distinguish. The output of AI is a number that represents a probability. It's not an answer, it's a likelihood. So by taking in several inputs from several domains, and these inputs could be huge. You can have a full 4K image as an input along with the entire movie set of Lord of the Rings, who knows? That could be your input. And it goes through this process of training to then understand that some probability is your output. And I think that it's very important to understand that when we're talking about how to use AI, because we have to understand that the output of AI that it's giving you is in itself not an answer, but a probable answer. Now, this is a grossly simplified diagram. It's not even fully connected. And typically, this would be in the heart of other very complex algorithms. But the result is a linear combination of nonlinear equations mapping an unknown function between potentially unrelated signals. Remember that. We are assuming that there is a relationship between the input and the output. It's unknown, but we're allowing the fact that the AI can give you an approximation to the function that gets you between those two domains in order to give you your solution. And most importantly, this solution will have error. It is unavoidable. There will never be, I shouldn't say that because I'm going to be proven wrong in 5 years. You're going to have a % chance. There will always be error, and it has to be understood what that error is because that error must be within the bound of the robot to be able to operate. If the error output by the AI gives something unsustainable to the robot to be able to do its task, the robot will fail. So the AI has to be able to give you error that's bounded within a certain domain that allows the robot to still complete what it's trying to do. And critically, different modalities create different error domains. So it's not just a matter of you train the AI, it's how you train the AI and what data you use in order to make sure that the output probability is within the limit of success to make sure that you're going to succeed. So we've talked about AI, we've talked about robotics, let's now merge the two together. So for each of that loop, the sensing, decision-making, action, AI has different domains that try and help that to augment it. When we're talking about sensing, understanding the state of the world, this is typically the domain of cameras and integrated sensors. AI elevates vision into perception. So it's no longer pixels on a screen, it's no longer values between 0 and 255. You now have contextual understanding of what it is that you're looking at. So in this example, you can see the image has classified dogs and cats. You are now no longer just seeing the image, you are understanding the image. When it comes to decision making, determining what to do next to achieve objectives, this is the classical domain of state machines and behavior trees, but AI empowers complex decisions mired by ambiguous conditionals. Who here has played a chess game against a robot before? Because you are competing against AI. And the way that they tried to train these AI models is at first they tried training them against people, and the models were terrible. So then they let AI train itself, and now AI teaches us. So these are the sorts of areas where AI does really well, where there's a lot of ambiguous conditions, where it's unclear what the results of various actions are going to be, and AI helps you to make a choice that leads to the optimal outcome. And finally, actions, interacting with the world. This is the domain of controllers and planners, but AI allows for training and learning. Now, I mentioned that this is all under the umbrella of cooperation. And that one's a little bit more unique. That one's a little bit newer. I know that there is work that's being done in this area, but there's a lot of room to be developed on how do we cooperate with machines thanks to AI. The joke was made earlier that I shouldn't say things like, Siri, play Beach Boys. Sometimes it works, but because that is a form of cooperation, but that is only in one direction. That is you telling the machine what to do. And anyone who's worked with someone who they liked working with knows that cooperation does not go in one direction. Cooperation goes in both directions. So how do we implement AI to be able to do those tasks? And the modalities I'm going to be focusing on today, because otherwise I'll take your entire afternoon, I'm going to be talking a bit about sensing, decision-making, and then at the end, philosophize a little bit with you about cooperation. So as I mentioned, I'm a mechanical engineer. I like to swing hammers. This is not necessarily my work. So I've shown here the individuals who have done the majority of this work, Benjamin Jaffe and Nabil Ramesh, from our senior research scientist, and a GRA from Georgia Tech Lorraine. When it comes to trying to use perception to understand poultry, one of the methods that we've been exploring recently is this idea of canonical mapping. Now you can see in the pyramid there, canonical mapping is a subset of deep learning. The idea that we are trying to promote is that you can take a 2D image and relate it to the vertices of a 3D model. So as has been brought up here in the past, data is everything and training is hard. The more images that you have, the more images you have to train, and that is very time consuming. What we have found is that by doing this method, you can actually, well, potentially get away with training a very limited number of 3D models and then associating those 2D pixels to that 3D model. And this allows you to do all sorts of things in terms of deforming the 3D model in order to get understanding about its relationships, as well as bringing it together into a system that is a three-dimensional world. So that method looks like this. We scan the bird, and you can see at the top right, we have assigned vertices to that bird. You can then fit an armature, which is the same way that computer animation takes place. And using that armature, you can then induce deformations in that scanned model. So the benefit here is that you're only using one bird. You're taking one bird, you're scanning that one bird, and now you have potentially infinite number of birds that you can use in your training. With these scans, you can then simulate the model. These are not the simulations we use, but we have the models and I can do what I want with them. So the benefits of simulation is that you can vary lighting, you can create occlusions, you have understanding of camera intrinsics, and then you can apply physics to the models to have them do all sorts of crazy things like drop into dishes from the void. And you can simulate soft bodies, rigid bodies, ragdoll fluids, forward inverse kinematics. And throughout this process, you know every vertex location, you know every texture information, and you have relative armature poses throughout this. So using these simulations, you can now train on the simulated data, and one bird becomes as many birds as you could possibly want. Unfortunately, the results was only marginal success. What we were looking for was that rainbow pattern, and you can see that we have the beginnings of that, but the relationships are clearly not there. It worked well in simulation or on the trained birds themselves, but once we tried to extend that to other birds that weren't part of our model, there wasn't much success. This is partially what's known as the sim-to-real gap, where everything works great in simulation. You write a paper about it, you high-five your friends, and then you try it out for real, and nothing works. And this is one of the things that we've had a hard time overcoming, and something that we've been working on very closely over the past year or so. The next generation, instead of mapping directly from the vertices, we are instead doing something that we call feature embedding. Now, when you talk about ChatGPT, ChatGPT makes a decision. If it says, I'm going to storm the castle, it somehow knows what the term castle is. There's more to it than that, but that's essentially what's going on. It has a vector representation of the word castle. And because of that, there are other words similar to castle that it might pick that are close to that word. I am going to storm the house. I am going to storm the fort. These words somehow have relationship to ChatGPT where it can determine that some words are closer to the castle compared to other words like chair. Maybe chair is a very loose relationship. And this same sort of idea of contextualized data having relationships to one another can be used within the image domain to say that pixels that are learned have relationships to one another. So you can see there in that image that the bird on the left and the bird on the right, the bottoms are both kind of green, the tops are both kind of brownish red, and there's a color gradient in between there where the program is understanding contextually that these pixels are not just RGB, they have a relationship that can be understood in this higher dimensional space. This becomes far more prominent, and one of the things that allows us to do is to bridge different domains. So you see there are 3 drawings, or a painting, drawing, and a classical drawing, and then a picture of a tiger. There is a relationship understanding where the head is the head, the feet are the feet, the tails are the tails that can be understood by this system. I will mention that these are RGB images, but these are representations of many thousand dimensional vectors. And what it does is it shows that the computer system can understand these images in a way where it can contextually relate one to another. And that, we hope, will allow us to bridge this problem that we've had with canonical modeling to be able to turn one bird's training set, or a very small handful of birds' training set, into something that can generally be applicable. So more training, more ridiculous settings. And what we found is that it works for, at the very least, sparse feature matching. So you can see in this image there are points picked on the left side image, and then the bird was turned around, a new image was taken, and those points could be associatively found on the right side images, where a point on the knee of the bird is, again, found on the other image. Putting that together, and we have something that works better. It's still not perfect. It still is a little bit incomplete. But what we found is that we have much better results overall, and there are areas that do really well, and then other areas that perhaps for one reason or another are suffering. And although it's impossible to see in this image, in the green picture of the bird there, a vertex was selected that is then matched on the image right adjacent to it. So what we can see is that we've taken the pixels of this image of this bird and related it to a three-dimensional model that has contextual understanding of that bird. Moving on and talking a little bit about decision making, having all the pictures of birds are great, and I can use them for posters in my house if I so desire, but that doesn't mean that we can do anything with them until we have a robot actually able to interact. So I will mention that this has been some of the work with Benjamin Jaffe and Kamala Krishnan. Kamala has started working with us over the past few months and has done some really excellent work in bringing some of these ideas into the next level of robotic understanding. So moving on, one of the holy grail tasks is grasping so that a robot can pick up, move, and manipulate an arbitrary piece of poultry product. We are attempting to take some results that has shown good success on arbitrary objects and then apply it to the poultry processing industry. This begins with the 3D reconstruction of the mesh, very similar to how you saw previously with the canonical model. But now you can do it in place. So rather than training a model ahead of time and then going back and then coming up with new models or interacting with new birds, you can come up with a three-dimensional scan of a scene and then use this to construct a mesh that can be understood by a visual language model, which is essentially the cousin to the large language model that ChatGPT uses. And from this, if you have a library of grasp poses that are associated with known objects, you can then take those grasp poses and instead of associating them to geometry within the object themselves, you can associate them to features of that object, very similar to what was shown previously, in order to translate grasp poses from known objects into unknown objects. So we have an example of that where we're going to query a chicken breast. The system is going to be able to understand what that query means and to be able to select the voxels that are associated with that, and then from there come up with a list of poses that it thinks would be good for the arm to be able to grasp them. And you can see that in action here, where the arm takes that information. There's no live visual servoing. The images were done once and then the positions were assumed to be static. But the arm is able to take that information, go in, and then supposedly collision-free, although it bumps that plastic fruit there, grab the chicken breast and pull it over to the table. So what you're seeing here is we never trained chicken breast within this model. We never said, hey, ChatGPT, this is what a chicken breast is. What instead we're doing is we're learning embedded features that the system can recognize and associate grasp poses with that to be able to translate into how the robot should behave with unknown objects. And finally, talking about cooperation. So this is at the heart of what I'm trying to achieve with the grant from the USDA NIFA work. And really, cooperation begins with us cooperating with one another. That's my heartfelt moment of the day, where this work wouldn't be possible if it wasn't for the joint and combined effort of all the people behind it. But if we think about what cooperation is communication to achieve task completion. Now, communication has a very important element that goes often untalked about, especially within our personal relationships, and that is trust and understanding. How many people have gotten really, really mad at their phone this past week because it did something dumb? I can't be the only one. Yeah, your phone does something dumb, and you're like, we have all the technology in the world, and you're not just rotating your screen on me. Well, half the time I would argue that it's not that the phone is doing something dumb, it's that the phone is doing something that you didn't understand, or the phone didn't properly understand what you wanted of it. And because of that misunderstanding, trust was lost. The other half the time, your phone was just being dumb. AI will never be 100% accurate. Neural networks transform an input domain into a probability output domain, and it assumes that a relationship between the input and output domains exists. But what if that relationship is in itself a probability? We assume that these relationships exist because we have such an easy time doing them, or at the very least, after years of growing up as a child and then becoming an adult, we somehow magically are able to perform these actions. However, we have to understand that the system that's being output isn't a direct answer, it is a probability towards an answer. And if we have that understanding, then AI no longer needs to be 100% accurate. We just need to know what it is perceiving, and we have to understand why it's making its decision. And then as long as corrections are possible, then it doesn't matter if AI is 100% accurate or not. So in these two examples, we can see that the top of the bird is correct, and actually most of the bottom is. If I'm doing an operation that just needs to use the top of the bird, then I don't mind that the rest of it has failed. And I noticed this while preparing, although you can by no means see it on the screen. Around the green bounding box is a little tag that says that it is 99.95% confident that there is a chicken within that green bounding box. So once again, this is about probability, this is not about solutions. And again, on the right, AI has made a decision. Some of those graphs are likely to succeed, and some of those graphs might struggle. So long as I understand what the grasping position is and why it has made that decision, or at the very least, if I can intervene and correct it if necessary, then I can trust the AI. Because it is no longer a one-way street of me telling the robot what to do, it is the robot telling me what it's going to do and why. And with that correlated understanding, now we can work together in order to complete these tasks. So I've mentioned a lot today about robotics, AI, and poultry. These are three very disparate fields. Often AI and robotics get linked together as some sort of intrinsic couple that belongs together. And although I do think that there is a lot of overlap in terms of what they're trying to achieve and how they're trying to achieve it, robotics and AI are their own fields that deserve their own respect and understanding. Poultry processing would benefit greatly from audit-based solutions. I don't think there's anyone in here that would argue against that. And if you would argue against that, I'd love to understand your point of view. And robotics has a paradigm that enables complex solutions to uncertain environments, but it's not there yet. There's no robot in the world that can go up to an unknown environment entirely and be able to operate efficiently. But artificial intelligence creates connections between otherwise disparate domains. So maybe with the use of artificial intelligence and being able to understand how AI can be used, we can bridge that gap between robots being used as labor and poultry, which is in desperate need of labor. So with that, I don't know if we have any time, but if there are any questions, I'd be happy to answer them.